Hi, I'm Ben-Yaakov. This presentation is entitled Power Electronic Challenges and Solutions of eMobility. This is an English version of a presentation given at a power workshop in Hebrew. This is a very preliminary introduction to the subject. It's a short presentation, relatively short, about 45 minutes. So by no means does it cover all the aspects of the issue. Also, let me state that the devices that I'm showing, commercial devices, are really for demonstration only, and there is no endorsement or recommendation to any of these devices. So here's the outline that we are going to cover. There'll be an introduction, and then the power electronics in electric vehicle, a general view, and then we'll go into each of the components, and then I'll discuss the possible benefits of wideband gap devices like silicon carbide and gallium nitride. And then I'm going to show some initial tests on gallium nitride-based inverter. So what's the motivation for electric cars? Well, primarily it is economics. Now here shown is the emission, CO2 emission of internal combustion engine cars in Europe during the year 2013 up to now. And we see here that up to 2018, for each one of the manufacturers, it's about constant, while BMW is fairly high and then Toyota is fairly low. This is emission in gram per kilogram. Now, as you can see here, there's a drop here, or an expected drop, which is due to regulation. Now, in the European market, in 2015, there was a limit to emission set to about, I guess, 125 grams of CO2 per kilometer. But from 2020, the target is 95 grams of CO2 per kilometers. Now here, this graph here is the average of all these. And as you can see, the internal combustion engine is really far from this target. So the only way that manufacturer can comply with this target, and they do have to comply because there is a fine of 95 euro for each gram of CO2 per kilometer above the target. So the electric car is coming to cover the difference between the emission of the internal combustion engine and the electric car. There's also a bonus for cars that emit less than 50 grams per kilometers, and this would be electric cars. And the bonus is that each car is counted at 2020 as two vehicles, while later on it's like 1.5 on the average, which means that if a manufacturer has a total of X number of cars, so there is a benefit for the manufacturer to go into the electric car production, aside from the customer who might be willing or interested in having an electric car. So we have today the micromobility or mini mobility range. These are the scooters, motorcycles, and the mini cars. And then we have a full-size cars. And then we have also the commercial buses and trucks. And now we already see some of the aviation, in the aviation area, airplanes which are electric driven. Now in the mini area, or mini car, or mini micromobility, we're talking about power ranges of, say, up to 20 kilowatt, and typically the batteries will be up to, say, 100 volt, while in the full-size electric vehicles, we're going to see power levels of 250 kilowatt and above, if it's a car with high performance. And then the batteries will be normally 400, but there is a tendency to go to 800, and either directly or through conversion from 400 to 800. So here is a general picture of what is the power electronics involved in an electric car. Let's start from the charger part. We have the line, we have the charger, then we have the main battery, which is being charged. Then we have the inverter, the motor, which has some outputs like either Hall sensor and encoders. And then usually we measure the current goes into the controller, which is operating or controlling the inverter. And then usually there will be a connection between the main battery and perhaps an auxiliary battery, either 12 or 24 volt, and some possibility of power exchange between them. And very important is the battery management unit, which sort of keeps an eye on the main battery, tests it, and maintains it to be in good shape, and I'm going to talk about it a little bit later. So this is the general picture. Now there is a tendency today to have the charger on board. This is an onboard charger. Not only that, there is also a tendency to have the system bidirectional. That is not only from, as it's called, grid to vehicle, but also from vehicle to grid. That is that the car is capable of delivering or supplementing power to the grid. Well, the reason for that is there are some programs of sort of helping, let's say, the electric companies in a case of drop down or in case of shortage of power, so that cars will be capable of giving or delivering some power to the line. So this onboard charger today, most of them are in fact bidirectional. That is, they can go from line to vehicle or from vehicle to line. Other than that, of course, it's about the same structure. So let's start now with the motor. Today, most of the motors will be brushless and probably permanent magnets, although there are some motors today, some cars which have a brushed rotor, but the tendency is to go to a brushless with permanent magnets. And as we can see here, what basically we have the coils. This will be the stator, this will be the rotor. The rotor could be either inside or outside, and the coils are excited such that they'll push or pull the magnet so as to rotate it. Now here is an example of a modern motor. As we can see here, there are many more poles here, and there'll be more of course magnets here. This is the rotor, and the magnets will be here, and this is the stator, and these are the coils here. So this will be a typical medium power motor. Now, as the rotor rotates and it's moving toward the coil, then it induces a voltage, the so-called back EMF, and this is the sort of reddish line here. This is the back EMF of the three phases, and it's going positive and negative depending whether the flux is increasing or decreasing. The voltage is the phi dt. And what we would like to have is the current to be in phase with the voltage. That's the current, ideal current, and this will be achieved by exciting the coils here with an input voltage, which of course has to be controlled by the inverter so as to produce this current. Today, in most cases, it'll be a sinusoidal waveform for the voltage and current. The reason being that you'd like the motion to be smooth, to reduce the so-called torque ripple. That is, that the motion will be smooth and not jerky. And so therefore, today, the excitation will be such that by modulation, this will be a sinusoidal waveform. Of course, there is a need now for a control such as to adjust the phase of the current with the voltage, and this is the so-called field-oriented control, which I'm not going into in this presentation. It's a very short presentation, but this will be the main task of the controller, not only to generate the PWM and the level of the voltage imposed on the coil, but also the phase of this voltage with respect to the rotation of the motor. Now, in order to do this, the controller has to take into account the fact that as you impose the voltage to the coil, this will be representing the big back EMF. There is an impedance in between. So therefore, there is a phase shift between this voltage, and this has to be either measured or estimated, and then the controller has to generate the vector, so to speak, of the input voltage such that after imposing the voltage on this circuit, then the current will be in phase with the voltage. Otherwise, you'll have to have a much higher current so that the VA will be higher, the general power, so to speak. So there'll be reactive power, which does not add to the torque or to the power, but only increasing the current, and therefore the losses both in the motor and in the inverter will be higher. So this is now the inverter, which is responsible for generating the waveforms here and feeding them to the motor. And the inverter typically will be a three-phase inverter. Shown here is a IGBT. And then we have the battery connected to it, and it produces the so-called phase current. Now, the phase current could be much higher than the input current, because this actually, you can look at it as a buck converter, although it's an AC, but you have the battery voltage with the highest voltage available in the system, and then usually you'll generate a lower voltage with a current, which could be, and depending on the vehicle, up to a few hundred amps, like 200, 300 amps. And obviously, the current that you'll see here depends on the modulation ratio, the duty cycle. So say if the duty cycle is half, that is on the average you have a voltage, this will be AC, but a voltage which is half the input, then the current at the input will be half that of the phases. So this will be the structure, typical structure of a inverter. And if we now look at the requirements for the motor, this will be a typical characteristic of a motor. Say, in this case, it's a brushless DC motor with permanent magnets. What we see here is this is the torque, and the torque is proportional to the current of the phase. And then we see here the speed of the motor, which is proportional to the voltage, that is the EMF. So a voltage increases the speed, and current increases the torque, and the product of these is the power. So this is actually the maximum power that you can get here, because this is the maximum, say, torque times the speed. So this is the line of maximum power here. This is the maximum torque, and this is the maximum frequency. And the colors here are the efficiency that in this particular case is achieved. The red is very high efficiency. This will be, by the way, the area in which the average speed and torque of a vehicle. This will be during low speeds, high torque, and this is high speed, low torque. So, and as you can see at the edges, the efficiency goes down. This is not zero, this is actually 80. So 85, 80 here, the efficiency, and then again in this area there'll be high frequency. So the objective of the inverter is to supply the voltage and capable of delivering the current required for the torque. So what are the expected losses from the power electronics point of view of an inverter? So typically we have 3 half bridges. This will be a 3-phase inverter, And here I see I'm showing the phase current, in this case going in, but of course the current can be going in or out because it's an AC on the average, although it's being modulated here. But what is important is that the current goes either through the upper side or the lower side of the half bridge, and therefore at each given point the current is going through one element. So in the case of IGBT, we have the current going through one element on the average, and therefore the power will be the average, because the IGBT is characterized like a voltage drop during conduction. So on the average, I'm just calling V sub C, and then therefore what is contributing to the power will be the average phase. This is an approximation because this is still current dependent, but just as a first order approximation, we can say that this product is the total power in the leg. And then therefore per transistor, since it's an AC, so half the time it's here, half the time it's here, I mean the modulation, then therefore it will be over 2. On the other hand, for the RDS-on devices like silicon MOSFET, silicon carbide, and gallium nitride, which I'm going to talk about later on, it's dependent on the resistance during the on time times the square of the current, and then divided by 2 for each transistor. So these are the power losses of the inverter, and of course the elements or the switches has to be chosen so as to be capable of handling this power and then dissipating the power loss. And here are some examples of modern inverters. These are silicon MOSFET based inverters made by IRP system from Israel. And we see here a very mini one, which is good for scooters and small vehicles like maybe a bicycle. And then we have here a larger one and up to 1.5 kilowatt, and then we have an even larger one. This will be for up to 30 kilowatt. Again, this will be a silicon MOSFET based and a low voltage inverter. These are transistors in parallel. The voltage is low, so we can get transistor with very low RDS-on, and the phase current here could be like 250 or 300 amp per phase. As you go to a higher power level, we are talking about today about IGBT, although now they are being replaced, and I'll talk about it a little bit later. These are being replaced by modern or more advanced or recently developed elements, and in particular now the silicon carbide. But now we're talking about IGBT primarily. This is the sort of the classical approach. And here I'm showing a module by Infineon. This is a full three-phase bridge in a hybrid construction package, and it is water-cooled or liquid-cooled from beneath. And inside we do have 3 half bridges. Each one of the switches is actually built from 2 IGBTs in parallel. These are 2 IGBTs. These are the diodes. These are external diodes, fast diodes. We have here, so we have 2 here. This is the upper side, this is the lower side, and these are the 3 half bridges. Okay, so let me move now to the controller. I'm not going to discuss it very much, just to say that the controller is getting all the information from the motor, measuring voltages and current, and then generating the drive for the inverter. Now today, controller will be digital controller, so we have here actually the controller, and this is a typical controller. Actually, it's a product of IRP. Again, it's a small unit in terms of size area on the board. It's really small, but all the, I'd say, the wisdom is here, because this controller has to take care of all the operation, not only the inverter, but the protection, starting, stopping, and all modes of operation of a vehicle. This is just a DC to DC, and as you can see, it's a fairly compact and economical design here. This is just a connector here, and primarily you have a very small area. So this will be the controller, and as I've said, I'm sorry, but this is a very, very short presentation. There's no way I can go into all the details. And let me move now to the onboard charger, which is now very, very hot subject that many companies are working on. Now, the power level we are talking about today is between the 6 and maybe 25 kilowatt. Okay, this is of interest. And as I've said, there is a trend to have it bidirectional. Okay, so the purpose here is, first of all, to be capable of taking the power from the line and then rectifying it and feeding the battery, of course, per the requirements of the battery. And also, it has to provide isolation because in most cases, from safety issues, you don't want the line to be connected to the battery while charging. So there is an isolation stage in between, and then it has to be bidirectional. So typically we're going to have something of this nature. We're going to have the line coming in, well, there'll be a filter, EMI, etc., protection, a startup, maybe a inrush current protection. And then we're going to have a power factor correction, because at this power level you do have to have a power factor correction stage. And then there'll be an inverter for the other side, I mean for the reverse current, isolation stage. And then you have a high voltage battery which you are either charging or taking or discharging, taking the power and moving it to the line. And then of course there'll be this interconnection between the two batteries. And as I've said, we're talking today about, well, it says here 15, but already the targets are 20, 22, 25 kilowatt today. Now, typically the power factor correction today stage will be of the so-called bridgeless, that is without diode, with sort of totem pole. This is the name for this topology. It's very popular now. And I'm showing here a design by GaN Systems. These are two GaN transistors. I'm going to talk about them a little bit later. And these are, in fact, could be silicon transistor, because these are switched at the line frequency, just moving it from here to here so as to accommodate the positive side and the negative polarity of the input, while these are switching at the higher frequency. As you can see here, this stage is up to, say, 3 kilowatt, and we're talking about up to 99% efficiency for this stage by itself. And of course it's lower at the lower power and a little bit at the higher power. Now, I didn't mention that, of course, one of the requirements is for this system to be of high efficiency, and the targets today are 97, 96 for the total system. So each one of the units has to be very, very high efficient unit. Now, when you're talking then about this onboard charger, there are actually two ways to go. One is without an intermediate energy storage, and you need an energy storage because the power coming from the line is pulsating, because you have the sinusoidal waveform, voltage and current, so the product is sinus square. And therefore, if you'd like the battery to be fed by a constant power, then you need a intermediate power storage to take care of the extra power and then deliver when the input power is low. But if you allow which is not very recommended, but it is possible. If you allow the battery to be charged in a pulsating current, then you really don't need this power factor, this energy storage. And this is, of course, for a single-phase line. In the case of a three-phase line, of course, you don't have this problem because you are producing almost DC or theoretically DC. But normally the requirement for the onboard charger is for this to be a single-phase line. So one way, of course, is to add a capacitor bank that will store the excess energy when available and deliver it when the energy is lower. Or another idea that people have been exploring recently, and that is to sort of add a extra unit that will sort of absorb in lieu of the capacitor, rather than a capacitor, to have an active circuit that will be more efficient, and particular will not have a electrolytic capacitors that you need if you just use a capacitor bank, because the energy is very high and you would need a capacitor bank. But if, for example, you go to higher voltages here, then you can get by with a lower capacitance, which could be, say, ceramic or film, I should say. And here is just one idea, and there are many ideas around, and I just copied from a paper here, and this is the reference. So what they are doing here, they're actually storing the extra energy into a resonant circuit composed of these two capacitors and the inductor, such that the excess energy is stored in the resonant circuit and then delivered back. So this is one idea, and there are many ideas, other ideas around. And typically, the isolation stage between the input side and the output side will be a dual active bridge. So this is one solution that provides isolation and some gain also, so that you can charge the battery and discharge it. And say for a 400 volt battery, you need a range of between, say, 250 or 300 to 450 volt to accommodate with this unit. So this has to provide this isolation stage, both isolation and also some gain between the bus here and the battery. And here is the solution offered by Cree. This is a manufacturer of silicon carbide transistor. They are using a 1000 volt devices here, and it's a 35 amp per device, and this is 65 milliohm. We see here a unit of 6.6 kilowatt. This is again the front, this is the power factor. It's a bidirectional, again, power factor plus inverter. Here they are using apparently also silicon carbide for the low frequency toggling, and this will be, say, the high frequency. And then we have here a isolation by a CLLC, it's a resonant stage, resonant converter with a bridge at the input, bridge at the output, which again provides isolation and gain. But in this case, in order to improve the efficiency and not to impose the large gain range on the DC, on this resonant converter, they have a variable bus voltage here, so they can control the bus voltage. These are transistors up to 1000 volts, so this is a single line again, I mean a single phase, so they can go up to, say, 800 volt, and by this help this stage in providing the gain that is required, either charging or discharging. And here are some results that we can see. And this is in the forward direction, that is charging, and this is an overall efficiency of the unit, and this is for 250 volt battery up to 450. So the green is the 250 and this yellow is 450. We're talking about, again, the best would be 97, 96. And this is for the backward direction. In this case, there's no need to go. Usually the specification don't call for the full power, but rather to a lower power level. And here they're showing up to 3.5 kilowatt. And again, efficiency seems to be very, very nice, from, again, 250 to 450 volt battery in this case. Okay, let me move now to another unit here, and that is the battery management unit. Now, the battery management unit is required because the battery is one of the most important and probably expensive component, single component in an electric vehicle. It's very expensive, very delicate, so the proper maintenance and well-being of the battery is really very, very important. And the purpose of the battery management unit is, first of all, monitoring the state of the batteries to see how they are doing and if there is a failure. And then another major task is to balance the batteries. And the reason is that in a, say, lithium-ion battery, which is very common today, overvoltage will shorten the life. That is, if the battery is overvoltage or fully charged and then you still keep charging it, it's shortening the life, damaging the battery, and also it could be dangerous. So you have to make sure that in a string like that, and a battery, a lithium ion, has a voltage between 3 and 4 volts. So to achieve 400 volts, you need 100 batteries. And so each one of them is being now charged and discharged in series, and you have to make sure that none will be sort of discharged completely or partially discharged, while the other one is fully charged. So this is the task of the battery management unit. Now, there are two ways to do it, to do the balancing. One is a passive, and in this case, what you do, you sort of bypass or discharge a battery which is with a higher state of charge than the other batteries. You can do it either in general when the battery is in operation or in resting, or during charging. Another way is an active balancing, and that is that you move power either from a central unit to batteries back and forth, or from one battery to another. Of course, the battery management system is a story by itself. It's a big issue, and there's a lot of details, and there's no way I can go into it. Let me just say that the passive battery balancing, which is very popular, is based just on a unit that is monitoring the voltages, and also when required, discharging or bypassing, you might say, or discharging actually the battery by a resistor and a switch that will turn on when required by this battery management system. Now, as I said, a typical lithium-ion battery has a voltage between, say, 4 to about 3. So this is for 100% state of charge. So for 1% of the capacity, we are talking about 100th of this thing, which is 10 millivolt. So the monitoring has to be very precise. And of course, if you're talking about 100 batteries and you have to monitor this upper battery, that's not a small or simple task. So these units are rather sophisticated, or have to be sophisticated, and very accurate in measuring the voltages. And then there usually will be a need for a communication between the control, the local control, and a central unit. So these are required, again, to maintain the well-being of the battery. Now, of course, in this case, there's a problem of dissipation. You can't dissipate too much power, and so there's a need for a strategy of when and how to discharge the overcharged batteries. There are commercial units for that purpose. Here I'm showing a linear technology unit in which you can have either internal switches, or in fact you can connect an outside switch. These are the discharging resistor, it's a monitoring, a multiplexer A to D. Well, there is actually a digital processing going on here, and then there is the bus that goes out with the information. Now, each unit can accommodate up to, I think, 12 cells. So therefore, you need quite a number of these for a high voltage battery. So it's a rather involved system. And as I've said, unfortunately, it's a must in order to keep the battery running and without any faults. Let me now move to another area, and that is the technology of the switches, the materials that switches are being made of. Up to now, we've been using primarily silicon. This is for the silicon MOSFET and the silicon IGBTs. Now, the introduction of wide band gap devices like silicon carbide and gallium nitride opens the door to devices which have better performance, and therefore it is assumed that they are bound to replace what we have now in not the long future. Now, silicon carbide are available today to 1200 volts, 50 amp per unit, but there's already modules for much higher current. And the gallium nitride today are available at single units up to, say, 50 amp, 650 volts. So this is the current state. We're talking about January 2020, which is changing, of course, very fast. Now, if we look at the traditional, or what we have today, that will be a IGBT for the high power, and here again I'm showing the module, Infineon module, IGBT, 700 volt, 400 amp, and it is important to realize that there is a benefit to actually using devices with RDS-on behavior rather than a voltage drop behavior like the IGBT. I'm showing here during the on state the voltage across the device. Now, IGBT will be typically something like that. RDS-on, of course, it's a straight line, neglecting the fact that the RDS-on is somehow dependent on the current level. So let's just assume it's a pure resistor. So if I compare these two for devices of same power, or about the same power, what I find is that there is a cross point, and therefore, if we are at currents which are low, below this crossover point, then the RDS-on has an advantage. If we go to a much higher current, then IGBT has an advantage because the voltage on it doesn't increase as much as the RDS-on. However, what happens if we take some devices in parallel? That's something we must do at high power. There's no escape from it. So if I take now, instead of one device with a current I, two devices with I 1/2 of this current, what I see is the IGBT doesn't change much the voltage, but in the case of the RDS-on, the RDS-on over 2, which is the two RDS-on in parallel, has a much lower voltage than the IGBT. So therefore, the RDS-on type devices like silicon MOSFET, silicon carbide, and gallium nitride have an advantage over the IGBT in paralleling. And we can see it here. In the case of IGBT, we have here this, this is now the curve that I've shown, although the axes are switched. Here I've shown the voltage as the vertical and current as the horizontal, and here it's reverse. This is the current, this is the voltage. So this is say for a given situation, 200 amp, we have 1.25. Now, of course, we have to worry about the switching losses, and here these are the switching losses for the on and off. In the case of, I'm talking about the Infineon device or module, say 200 amp, we are talking about a total of about 11 millijoules, while the diode, during the time the diode is conducting, because the IGBT is a one-directional device, and in the reverse direction the diode is in fact conducting, we're talking about 1.2 volt, which is not too far from what we have here. So this is the picture of the IGBT. And the total power dissipation of this device is about 121 kilowatt, 1.2 kilowatt, when of course water cooled, and the case is 25, which is be impossible to achieve. So let's say it'll be a little bit lower than that. So if I just take an example, assume 200 amp per phase, switching losses are 11 millijoules, and then I have the conduction losses 250, and then we have switching losses of 110, I guess. So we have 360 watts per leg, so it comes out to be a total of 1 kilowatt, which is the upper capability. So this will be the upper limit of this device. I'm talking about 400 volt line, and switching frequency of 10 kilohertz, which is okay for motor. I didn't say it, but there's no advantage in feeding very high, or modulating the inverter with very high frequencies, because in fact you lose, because the losses when you feed a modulated signal to a motor will be very high at high frequency. 10 to up to say 50 kilohertz is at most you'd like to go with today's motor. Now, if I'll parallel now, if I want parallel to get to 400 amp and I parallel 4 units, I see that rather than 1.5, 1.6, I can get a little bit 1 volt, and the gain in the voltage drop is only 1.7. But of course, if I'll be paralleling 4 elements of RDS-on type, then it'll be RDS-on over N, and so it'll be much lower power. Now, as I've said, there are already some modules with silicon carbides, and here I'm showing a Cree module. This is a 1200 volt, 450 amp. This is for DC, of course, not switching, but we're talking about high power, so it'll be for an inverter, it'll be to 200 to 300 amp per phase. This is a half bridge only, it's a half bridge, and the total resistance is 4 milliohm of all the devices. And here we can see this is the half bridge, and we see we have 1, 2, 3, 4, 5 transistor in parallel, okay, for the high side and low side. This is from this paper which I'm referring to, which is presenting a 300 kilowatt 3-phase silicon carbide inverter based on this module, okay, that we are talking about. And here we see waveforms, which are very nice. This is 50 nanosecond per division. This is 100 nanosecond per division. This is for the low side. This is the high side. In general, we see a very little overlap because of very high speeds involved. But in the case of the low side, for the probably when the high side is in the reverse direction, we see a little bit of a overlap here. Now, what about switching losses? Well, unfortunately, in the case of the silicon carbide, it's not very good. We see here switching losses for 600 volt, and let's say for 200 amp, we are talking about 10, a little bit less than 10, say 8 millijoule. And in the case of the IGBT, we have at 200, we have here, let's say 3 plus 8, so it'll be 11. That's the 11 that we talked about later on. So it's not a very large leap here in terms of switching losses. But for motor drive, this is not so bad because, as I've said, the frequencies we are working at the modulation frequency are fairly low, and of course the total loss is this number, millijoule times the frequency. And if the frequency is not that high, it's not so bad. Gallium nitride is much better and in this respect, but unfortunately we don't have modules today with gallium nitride. We have single units. Now, for automotive, there have been many standards developed, but they are really for IGBTs, not for silicon carbide and gallium nitride. There is a process now of developing the standards for these modules. Now, in the IGBT, these are very severe and very highly demanding requirements. For example, it is required that when you have a real short of the high side and you turn on the device, nothing will happen for a certain period of time. Of course, this will be a short circuit capability withstanding. And IGBT are okay because IGBT sort of saturate. That is, although you impose the bus voltage on it, you turn it on, the current is sort of saturated to a given level. While in the silicon carbide and the gallium nitride, you always are in the, at least today, in the linear region, so the current goes up and up. So therefore there is a problem with these devices in terms of robustness as compared to the IGBT. Here, there are some studies made on silicon carbide. We see here the capability for the so-called Avalanche, which is another aspect. That is, what happens if you charge the inductor and then you turn off the transistor and let the inductor voltage go up, and then eventually it'll clamp. Now, in the IGBT, there is a sort of a Zener effect and capability of absorbing the extra energy, which is less in the silicon carbide and even less, more or less, than in the gallium nitride. But in this particular example, there is a clamp here by the transistor to about 800 or 2000 volt, and this is, as far as I remember, a device of 1200 volts. So it's clamping to a higher voltage for a given period of time. Of course, if the energy is very high and persists, there'll be a breakdown. So what about the gun? The gun, in terms of short circuit avalanche, is really less robust than the silicon carbide, and certainly much, much less than the IGBT. So to overcome it, there is a need for, on the one hand, the fast current sensing and turn off of the device. That is an external circuitry that will protect the device when you have a short circuit. So you can actually do the same experiment like this, say, but the transistor will have now an auxiliary circuit that as the current will go up, it'll turn it off. Obviously, you have to be careful when turning it off, because then if it's too fast, you might have an overvoltage. So there's another requirement of an overvoltage snubber in some cases, so that you'll not exceed the maximum voltage. Again, the gallium nitride is sensitive, and if you exceed it, it'll break down. And finally, I'm going to show some very initial results of a inverter 4 motor drive, and we have here a parallel of 6 units of gallium nitride. These are units made by VISIC, it's a company VISIC, and this is one half bridge. This is the high side, this is the low side. This is the same board from both sides. Of course, there's a heatsink here which is being removed. The heatsink is liquid cooled. And here from the other side we see the driver. This is the driver. And when operated as a buck converter, this half bridge, we see here typical performance. We see this is a level of 13 kilowatt with a bus of 400 volt. And the RMS current coming out is about 70 amp here in this case. And you see that the efficiency of this unit in this point is above 98%. Now, the very important question is the power sharing, and in particular as to whether the junction temperature is the same. And what was done here, there's a hole, and we are actually looking at the belly of each of the transistors. That is from the other side here, there are holes, and we look through the holes and see the belly of these transistors. And here are the measurements, and the difference in temperature is no more than, say, 3 to 4% of degrees centigrade, which is, of course, very good. And we've been using the controller that I've shown earlier for IRP, and driving this motor with the 16 pole, and these are the basic parameters of the motor. And here we see the setup. This is the dynamometer, the dyno. This is the inverter, water cooled, and the motor. And here's there's a power supply, and there's the load actually feeding the energy back to the line. This is the control stage. We have also an outside control stage. And here's a typical result. Here we see the voltage on the upper side and lower side of one half bridge running at 20 kilohertz. In this case, it's 80 amp. This is the phase current. And then here we see a zoom of the same picture. This is, in this case, 300 volt bus, 20 kilohertz, and we have here at a point of 143 amp per phase. This is the current, but of course we're at a zoom level. And here are the voltages, as you can see, very clean voltages of the upper transistor and lower transistor. So this brings me to the end of this presentation. I hope you found it interesting, and perhaps it will be useful to you in the future. Thank you very much.